try today.
Hello everybody, can you hear me? All good? Great, great, great. So, because this is right after coffee break, I hope I can entertain you enough so you don't fall asleep. Right? This is going to be an experimental talk. Right? It's going to be plenty of colors so you guys don't fall asleep. Okay? So, first of all, I would like to thank Dimitris for two things. First, because of this beautiful place, it kind of reminds me of home. If you type in Google Veracruz, that looks like great here, beautiful place. And the second thing is, this project that I'm going to be discussing today comes with a collaboration with him. It comes from many of his ideas. And now we're trying to do is implement those beautiful ideas in my laboratory in Stony Brook. Right? For all of you that don't know where Stony Brook is on Long Island, which is about an hour from downtown Manhattan. So it's kind of good, kind of bad. All right? So what I want to tell you today, basically, is something that I think is somehow a novel idea, okay? And I come from a different community. I do come from the quantum communications community, and I do a lot of experiments with quantum memories. We talk about quantum repeaters, lag-matter interfaces, storing qubits, and doing things like this, okay? And then what I realized by looking at the literature is in many of the proposals for quantum simulation, people are trying to actually solve the same problems that my community is trying to solve. Okay? So basically what I want you to imagine is our most important idea, right? We want to build a quantum network, and that this quantum network should be able to both store information in memories, right? As we have over here. Right? We should be able to produce photons and encode information in these photons, and then store it into quantum memories. Quantum memories should be able to talk to each other along the lines of, for example, what Professor Soler told us in the morning, right? And we also want to be able to send this information into qubit gates that are able to operate, qubits that were stored here, right? And then the two main problems that we have to solve, right, in order to get to that dream over here, is basically the creation of quantum lag-matter interfaces that do work at the single photon level with low noise, okay, with high fidelities, for example, if we're doing qubit operations. And we also want to achieve devices that have single photon level non-linearities, right? Photon-photon gates. And what I'm going to show you in the rest of the talk, you will see that these two problems are actually the problems that we should also solve in order to produce a quantum simulator that works with atoms and light. Alright? So then, what I'm going to do in my talk, in the first part of the talk, I'm going to give you kind of like a catch-up on what we're doing, the systems that we're working with. And then in the second part of the talk, I will show you how we implemented the ideas of the Angelakis group into our experiment. Okay? Alright, perfect. So then the first thing that we're going to do is we're going to do a very quick review on electromagnetically induced transparency. So Professor Soler already today in the morning talked about quantum interference, right? In a different setting, of course, to achieve these timers. So basically, there are two ways to see electromagnetically induced transparency. The first way is basically what the experimentalists do, right? You just shine lasers into things and then see what happens. Alright? So then for us, EIT, basically we need two lasers, right? We need to address the right transitions of rubidium atoms, for example, here and here, create a lambda system. And then what you see here on the left, right, we're basically scanning one of the lasers. We can actually scan the absorption lines of rubidium in this case, right? And if you position the second laser, please remember this name, is what is called the control field. Right? To precisely a quantum interference phenomenon, we're going to create a whole absorption. This is this peak that you see right here. Therefore, the name of the feature, electromagnetically induced transparency. This feature, apart from being actually kind of nice to the eye, is very helpful to do actually many things. One of them is, for example, storing light, which is related to the dispersion changes that this abrupt change in the transmission conveys. Okay? For the purpose of this talk, because most of you are actually theory, I'll give you also the theoretical version of EIT that will help us to understand what we're going to be doing in the lab. Okay? So then basically, I'm not going to do a derivation here. Basically, this is the basis of what is called quantized EIT, in which you send a quantized field. Think about a single photon, maybe carrying a qubit, and how this control field, which is a classical field, modify the properties of an ensemble of atoms so that you can prepare it and then store that photon in the ensemble. Okay? The only thing that we need to think about here is that, and this is the idea that I would like to convey, at the moment that the photon is propagating into the atomic medium, we're going to create a quasi-particle that has two properties, is at the same time light, but also because it's exchanging energy at all times with the atoms where it's traveling, it's going to also have a part that is atomic. Okay? So then Professor Fleischhauer came with a very fancy name to what this thing guy here is. Right? So then this wave function that describes, you can see here, this is a quantized electric field, and this one here is what we call the spin wave. Right? So you see that at all times, this quasi-particle is either light or atoms, excitations, or both. Okay? And then the important thing is basically you can, in time, manipulate which part of this the polariton is, so that we can dynamically convert between having all light at the moment the photon is impinging in, to actually have full atomic part at the moment you switch off this control field here. Alright? So please keep that name in mind. Dark state polariton. Dark state comes from the EIT physics that we use as well. Okay? Alright? So then just to give you a picture about what's happening here, right? So basically the experiments that we perform in my laboratory, we set a single photon, or let's say a temporary coherent state in which the pulses contain on average one photon, then we put the control field, right? And then we have our atoms here. And then what we do is, exactly at the time in which the photon is propagating here, right, we're going to have most of the polarity is going to be in the form of length. Then at some point, remember, we can do this dynamically. What we're going to do is we're going to switch off the control field. You can see that in this picture there is no control field anymore. And then we're going to transfer to a stimulated adiabatic passage process. We're going to transfer the excitation that was present in the electric field to an excitation in the atmosphere. Right? Fancy names for these. People call it spin waves, people call it magnons. Alright? So then that's just basically a way in which the spins of the atoms are oriented depending on the temporal profile of the photon that was stored. And then of course what we can do is reverse this process. This is what is nice about this. And then what we find is if we put the control field again, right? Then our excitation, you see here, is going to now turn back into light, and then we can put it out of the system. So then for us, in the quantum communication community, our target is always encode qubits into these photons that are coming here, then do the storage process, retrieve the qubit, and then compare the fidelity between the output and the input. And there are some thresholds that have to be beaten in order to claim that your system is quantum. Okay? So there are two ideas here we have to remember because they're going to be useful for the remainder of the talk. This plot here is a typical storage of light experiment. Right? Basically, this is the input. Okay? This can be containing one photon on average, or be exactly one photon. Then this is when the control field is switched on. This is when we switch off the control field. You notice here, these processes are not perfect, right? Because the photons are actually very long, and then we cannot compress the entirety of the photon into a tiny atomic unit. Okay? So then basically, this one here is what we call the leakage. That's basically light that didn't undergo any interaction. You see that right here, there is no light, but the polarity still exists. It's basically in the form of full matter, and then we can then retrieve it, and this is what we want to analyze here. Okay? So then, this new form of quantum simulation that we would like to do with these things, right, is now based on the interaction of the dark state polaritons that are actually coming of the system here. What kind of equations these dark state polaritons obey? Right? And under which conditions we can actually observe the dynamics of those equations while measuring the output of our photons. Right? Most importantly, this works if you have single photons, right? So either classical or you send single photons, therefore you have access to unification and creation of operators that have influence that you want to do, which is important. Alright? So this is basically the flavor that we do in my lab. Okay? This comes from the fact that, say, remember we want to do quantum networks and we want to be able to have many devices operational. If we want to be quantum repeaters, we need like hundreds and hundreds of them. Right? So then basically, starting like 3 years ago or so, we actually put ourselves the high task of making these devices, these light matter interfaces, operational at room temperature. Alright? As you have many of experiments here, you need to cool down everything if you want to avoid incoherence. Right? In this experiment we are doing totally the contrary, we're actually warming up. And what I will show you is that now we have the systems operational completely at the quantum level, and then we can perform operations akin to any cold atom system. Right? And that's kind of cool because then, well, I mean, if you have some money, then you can build 10 of them for the price that you can, for example, build a Bose-Einstein condensate or something. Okay, so this is a technicality, but it's important. All right. So here I show you the system that we do. This is basically what we look in the lab. So what I described very rapidly is the characteristics of the experiment that we're doing. In this experiment in particular, we want to store qubits, right? Then we're going to relate this to the actual purpose of the talk. Right? Basically what we said is that the photons here, in this experiment, this is what is called a dual rail experiment. This is what is depicted here. Basically the photon is split into two parts, right? If the photon is carrying a qubit of the form H plus V, for example, then the H part goes into one of the rails, and the V part goes into one of the rails. Notice though that they are coherent with each other because they come from a qubit, right? So then what we do is we drive two of these rails in the hole here, right? There is the atoms are inside this. I like to call it a beer can, a really big beer can. And then basically what we want to do is we want to independently store the two modes of the qubit through this dark state polarity of physics that we just described. All right. The caveat here, of course, because we do these experiments at room temperature, is, can you imagine, in order to fulfill the phase matching conditions required to do this experiment, we're actually impinging one single photon that carries a qubit and is accompanied by about 10 to the 12 photons per pulse in the control field that, of course, are required to do the storage. So you have to be able to remove them from your measurement, otherwise you're actually going to kill your detectors every time you do the experiment. So basically what you see here in this side of the experiment is the frequency filtering mechanism that we use to precisely measure only the one photon here. Okay? I'm not going to go into the details. Basically the only thing that I want to tell you is that many of the things that we have discussed in this conference, we have used them, right? And one of the main things is people actually told me that it's not possible to build quantum memories at room temperature because of the noise. Okay? And then, well, I normally don't believe when people tell me stuff, so then we tried to do an experiment, and of course it didn't work. So then I wanted to do it again and again until it worked, and we made it work. So, well, that's one of the things. And how do we make it work? Basically, what we have to do is, here you see this is the atomic system that we are considering, and because we are operating at room temperature, we would like to investigate what are the noise sources that contribute to infidelities when we do the storage process. Okay? So basically what we have to do is we have to do a full master equation simulation that basically includes all the atomic levels that are addressed. Most importantly, because we are at room temperature, we have to see how these full master equation results that relate to not moving cold atoms actually transfer into atomic motion and how these systems, right, can be translated into room temperature operation. Basically, the plots what we can see, for example, here, this plot is basically telling you the number of photons that the system produces when there is no input. Right? And that's what is called the background. Background is produced by nonlinear processes when the system is at room temperature. Okay? So basically what we have to do is we have to do a research of the parameters of the system and then basically find a sweet spot in which you produce the least amount of background while still having the highest efficiency in your quantum storage process. Okay? By doing this, when we get plots like this, this is the equivalent of the plot that I showed you for storage of light. This is at the single photon level. And at the single photon level, the signal to background here is about 6, meaning that for every 6 photons that you detect that are good, you detect this one that is bad. Okay? This result is very interesting because it's the first demonstration of unconditional quantum memory operation at room temperature. Okay? And we just got it like basically a few months ago. Alright? And then the message from this, right, and then so we can actually get into the purpose of our talk, is that now our systems, right, operate with a fidelity is about, let's say, close to 90%, right? Close to 90% at 330 Kelvin. It means that we can perform quantum memory operation akin to any system that you want, Bose-Einstein condensate, single atoms in cavities, again, liquid crystals, right? So we are operating already there at 330 Kelvin, okay? So now the question will be, good. This looks good. This means that we have already a light-matter interface that operates at room temperature at the single photon level with high fidelities. Can we use this to build a quantum simulator that uses photons and atoms? Right? And these are the questions that now we will describe in the following slides. Okay? Just an advertising. People were talking today in the morning about cascading quantum devices. So this is an experiment that we have performed in which we actually did cascade two of these room temperature quantum memories. We basically store one qubit, we retrieve it, then we send it to another memory, and then retrieve it again. So you can think of it that by having many of these, that is actually allowed now by having this room temperature two devices, you can start thinking of creating quantum networks in which you can look for topologies that are not trivial. Okay? Great. So then, okay, now let's talk about this. How are we going to build this EIT-based quantum simulator? Okay? So the first slide that I have to show here is basically the trick is to go from one of these EIT systems that we use into using many more lasers. Okay? And what I will discuss is basically the recipe that we have to do to achieve this. So then remember what we discussed before. We have a lambda system, right? These are our photons, and this is the control field that we want to achieve. Okay? So then this paper is probably of interest for all the community in quantum simulation, right? It's basically providing us with the details that we have to follow in order to use the concept of quantum memories and matter interfaces to make this a quantum simulator. Alright? And basically the idea is, instead of only having one lambda system, we actually have to build many lambda systems and then look at the interaction between these dark state polaritons that are built in these many EIT systems together, and then see what kind of equations are obeyed by these components. Okay? So then basically the proposal, and then just to give it short here, relates to now having for example, what we can do is we can send one photon in the input, and then we can have 4 control fields. This is what you see here, 1, 2, 3, 4, right? And then basically by creating 4 simultaneous EIT systems, we're going to actually create a system that has 2 dark state polaritons as opposed to only 1. It is the interaction of these 2 dark state polaritons that will give rise to the quantum simulation that we want to do. Okay? Notice this paper is actually very cool, all right, by Professor Fleischhauer. Okay, it's a very seminal paper. Okay, I am not a theory person. I will describe this relatively briefly. So basically, there are 2 ideas that we have to put here, right? When you have a system that now has these 4 EIT independent systems, this is what is called a double tripod system. Okay, so the double tripod system has now 2 dark state polaritons. Remember we talked about dark state polaritons as being the quasi-particles that have electric field and spin waves. In this particular case, you already see where the dynamics come from. In this case, there are 2 spin waves, right, associated, because now we have 3 ground states that are being addressed by the system. Okay? A fancy name that people used to describe this is basically you can describe it as a 2 vector here that contains these 2. These 2 are what is called the spinor components. Okay? This, what is called here, is called spinor slow light, like spinor of slow light. Okay, so basically, algebraically, it behaves like a spinor that you guys are very familiar with. Alright? The heart of the calculation basically goes to say, from the basis of the Maxwell-Bloch equations that the system should follow in a quantized basis, you can then derive an equation that governs the dynamics of this spinor of slow light. Okay? The main result of this, of course we cannot derive it, but we're just going to say, is that the spinor now obeys a drag-like equation. Okay? So then, this is the first idea that we have to communicate. By doing these multiple EIT systems, and then we program with single photons, now we gain the possibility that by understanding the dynamics of the dark state polaritons in the system, we can actually simulate physical systems that obey the Dirac equation. Okay? Very important here, right? You see from these equations, the thing that is important is that now the speed of light in this, for example, relativistic dynamics that we could simulate now is given by the slow group velocity that the photons, right, the polaritons follow in the medium, right? And there is also the possibility of adding a mass, right, that now depends on an atomic parameter. This guy here, delta, this is actually very important, which is basically at the tuning, and it tells us how far the lasers are from resonance with the atoms. Right, so then we have now 2 very important tools, basically. The group velocity can be controlled with the intensity of the control fields, and this new term here that basically can give rise to different dynamics is controlled by the position that our lasers have with respect to the atoms. Okay? Here I'm going to make a link, right? In the arena paper that we are describing here, they say the secular approximation is well justified in hot atomic gases. Okay? That's the theory's point of view to say you can make this experiment work in room temperature systems, I think. Okay? So then, well, because we have already developed this room temperature quantum-like matter interfaces. Now we actually face the possibility of producing this, okay? So then basically, in the next slides, we're going to discuss how we're going to do this. Okay? So this is a roadmap of what we could possibly like to do. So then 10 years from now, when we meet again, you can tell me, you didn't do anything, or you can tell me, you did some stuff. Okay? So then this is really like a roadmap. Okay? So then basically, what we have to do first, right, is we have to develop this quantum-like matter interfaces. Check. This one we have. That's a good. Right? We know from theory that under certain circumstances, these polarities will obey the 1D Dirac equation. So we have a means to actually do quantum simulation. And second thing here, remember at the beginning we talked about creating optical nonlinearities triggered at the single photon level. If you were able to do this in an atomic system, which is the thing that people are doing at the moment, they're trying to find ways to actually create this, we can enrich the number of Hamiltonians that could be in principle simulated with these dark state polarity systems. Okay? Just to give you a flavor of this is mostly the work of Dimitri's here, right? Basically by adding optical kernel linearities at the single photon level, you can increase, right, the reaches of the Hamiltonians that you can do. People talk about simulating group repairing, nonlinear Schrödinger models, quantum Hall effect, and bosonic theory models, right? And basically the question is, what can we do now? Right? What can we do now is, if we don't have the single photon level nonlinearities, more on this at the end of the talk, what we have to do then is to simulate models that do not require nonlinearity, and this is provided by this guy here, the Jackie-Brevin model, okay? That some of you have been familiar with. This was introduced actually in one of the previous talks in photonic systems, okay? So, all right. Okay, so then basically what we're going to describe now is what are we going to do with this Jackie-Brevin model. Okay, so some of you might know this. As I said before, I'm an experimentalist, I'm not a theory person. But basically when we have this Jackie-Brevin model here, right, this is a one-dimensional Dirac equation, right? And basically there are several properties that are very important because, for example, in this equation we have this scalar field, right? If this scalar field obeys this Klein-Gordon equation, we're talking about electricity dynamics here, right? Then this forces the creation of this zero energy, right? Zero energy, yes. And basically, this is kind of like the beginnings of what is called topological protection of modes, right? So then basically, this model is historically very relevant, right? Because even before many of the experiments and theories developed in modern times, it already kind of was a precursor of topological instruments, right? That kind of really tells you the reaches that this could have if it's done properly, okay? Now, here basically, this is something that I learned when Dimitri's was in Stony Brook in the summer of 2013. We were actually discussing his proposal. In his proposal, we are trying to use this double tripod system that we discussed before. That's the one that obeys the one-dimensional Dirac equation. And the question was, how are we going to make it in reality? Okay? So then there's a few things that we have to remember. Right? So this obeys the Dirac dynamics. In his paper, Dimitri's and his group actually proved this, right? It's basically a similar result to the one that we saw from the flash hour paper. Most important thing here is under certain conditions, you can make that Dirac equation look exactly like the Jackie-Brevin model here. And as we said before, right, there are two terms that are of relevance. The speed of light can be now tuned optically by modifying the group velocity of the polaritons. And we have now this term here, delta, that refers to the position of the laser with respect to the atomic transitions, right? That now fills the purpose of this mass here. Okay? There is one thing that is very important, okay? And then basically, if we really want to probe whether or not the system is providing us with Jackie-Brevin model physics, right? This has to be coupled to a soliton, right? And if you couple this to a soliton, then the system should evolve into a topologically protected mode. Okay? So then basically this we will discuss in a little bit. How is that we can produce this soliton, this kink, and be able to, in our atomic system, resemble the dynamics of these topologically protected modes. Okay? Good. So now what I'm going to do here, now we're going to talk about experiments. Okay? So then, as we said before, the key idea, transform these EIT systems into quantum simulators is to, instead of doing only one EIT at a time, now you're going to do simultaneously many of them. Okay? And then how we achieve this? By actually using lots of lasers. Okay? So then here I describe very briefly what we do. You can already see here, this frequency here is going to be the one in which we're sending our photons. Okay? So that is color red. And then what we're going to do here, you see we have two control fields, and this is what is called a tripod, right? Because it has 3 feet. This is basically what we're doing here. Right? So EIT system number 1 is this one here. This is what we're saying here, right? Color coded. Then we have this EIT system here and here. Right? This is EIT system 2. Alright? Different to the proposal in these papers, now we have to do the properties of the iridium atoms we are working with, and in order to achieve this simultaneous double tripod system, we actually have to use another excited state in the iridium atoms. And in this excited state of the iridium atoms, we are going to create the second tripod system. Notice what is important here. The two tripod systems are sharing ground states. That's what actually makes the system work. Okay? And then here we have now the second tripod system. You see this green, this is EIT4, and then this one here, the green and the blue, here was this EIT3. Okay? So there are two important messages that we have to understand here. Right? Basically, remember, we always talk about, when we talk about spinors, we need to have two components. Right? In this implementation that we're doing here, one of the components is going to have a wavelength of 780 nanometers. This is what is called spinor component 780, which is basically the wavelength that you use from going to here to here. Technically, people call this a D2 line of iridium. Right? And the other component of the spinor is going to be in a different color, which is 795 nanometers, which is basically the D1 line of iridium here. Okay? So then effectively to do this, you need 5 lasers. One is a single photon, or could be a single photon. The rest are classical sets. Okay? Just here, a tiny little cartoon that helps us understand more or less what's going on from a very intuitive picture. You can always think about this double tripod system as two independent EIT systems, right? In which now you have here the ground states are no longer the ground states of iridium here, but one of them is actually a superposition of these two ground states here. Right? This is the one in the red, this system here. Right? So this is one of the components of the spinor. Here we have the other component of the spinor, which is blue, this guy here. But they talk to each other. They crosstalk through this tuning that we're going to do here. Okay? And then so what is important is this tuning that basically tells us the frequency difference between these lasers and the ground states, right? Is what is going to create this crosstalk. And through this crosstalk, we can then claim that we are seeing some dynamics, maybe direct dynamics. Okay? So then, well, I gotta say, this is work in progress, so what I'm going to show you today is basically the actual progress that we have so far. And then what we have to do in order to build this is we have to probe the system independently for each of the EIT systems. So in other words, we have to see storage of light for the 4 EIT systems independently, and then once we have seen this, then you can shine all the lasers at the same time, and then things evolve. Okay? So then this is what I'm going to show you in the next slide. Alright? So basically this is how the experiment works. Right? So we have 4 lasers, alright? And from one of the lasers that we see here, right, we create our probe field by basically switching into optical modulators and attenuating this laser to basically the single photon level or so. Okay? Part of this laser comes into another AOM, and this becomes what we call the control field 2. We have a second laser. The second laser is important, is phase lock to this first laser, and it is this phase lock, basically determined by the electronics, that determines this factor delta that provides the dynamics of the system. So then we can tune that factor delta very, very precisely to within maybe 10 hertz or so. So that's kind of the level of precision that we have there. Okay? Basically here, right, we have the first tripod system, and then what we're going to do is basically we're going to have a twin system over here, right? We are creating two control fields, right? And then what we're going to do is we're going to send photons, right? We're going to store photons akin to what I showed you already in the previous slides. So then we're going to create one spin wave just using one EIT system. And then what we're going to do is, after creating that spin wave, we're going to read it with each of the control fields. right? So then independently we should be able to retrieve 4 different colors, right? And this is what we're going to do next, just so you have an idea how these things look in the laboratory. These 4 lasers here and these 4 lasers here, right? It's basically one full optical table of electronics just to maintain the frequencies of the lasers very stable, right? And then, well, we shine these into our beer cans here, these room temperature systems, and then what we can do here at the end, this is important, we can make measurements of the fields that are coming out of the memory depending on the color. Right? If you use this compound tomography, you can always beat these with the same color that you're analyzing, so you can tell what's happening in time with the color. Alright? So in the next slide, I show you precisely what we're measuring now. Okay? So then here, this is what it's telling you, this is the input, right? And then what we can do is, if we switch on control field number 1, right? This is it's kind of like yellowish trace here. That means that we can see storage of light, so that works very nicely, right? In the second experiment that I showed here, we send the same input. We use control field 1 to store, but then in order to retrieve, now we use control field 2, right? So then we are reading this spin wave with a different color. So then the output, this red one that you see here, comes actually with a different color, okay? You can do the same thing now for the other tripod system, the one that operates in the D2 line. Here we do exactly the same thing here. Same input, store with control field number 1, and now we retrieve the control field number 3, and then you see here, that's the effect of the storage, alright? You can already see for the second tripod system, this is a little bit more lossy, right? Because you use more absorption in the system as you go along. Now, and the important thing here, right, and this is kind of like the main result of what I want to show you today, is once you put all the control fields at the same time, yeah, you get this guy here, right? And in this one here, you actually have now the 2 spinor components, and this is exactly the temporal behavior of this guy here is what we can then consider the solution to this Dirac-like equation. Alright? So now the question is, how are we going to then get access to this temporal profile that is telling us that the spinor components are interacting, so then we can then claim that they are following this Dirac equation. Okay? So then what we're going to do, and this is kind of interesting, we're going to change the storage time here. So the time that it takes for the fields to be applied on, then off, and then on again. And then what is going to happen is, because one of the systems is going to have this tuning that we put in our electronics, is delta, and the other system is not going to have it. The electric fields, right, so the photons that are coming out of the system will evolve with a different phase, right? Depending on how much they are propagating in the medium, this phase will increase and increase and increase. So we should see a beat, right? We should see a beat node between the 2 spinors in order to make a claim that then Dirac dynamics are followed. Okay? So this is what we do here in the next slide. Right? This is actually very, very preliminary results. My students hate me because I had them measuring this just before the plane that was coming to Crete started. So this is very, very recent. Here we're basically, this is just the 3 part, right? And then what we do is we increase the storage time, okay? And then so normally what you will see is that as long as you increase the storage time, then you should see an exponential decay of the energy, right? The energy being the rate between the area that we have here in these pulses and the area of the original input that we sent. I mean, it's not really evident from here, but I think you can already see here that this is not the case. This is not only a simple exponential, there is an oscillation on top of it. Okay? And this is what if you extract this, basically you analyze the area of this compared to the original input. This is what we call the storage efficiency. Here we measure for one particular output, which is the spinor component at 795, and then you can see that now there are here these oscillations. Okay? These oscillations are the proof that the 2 spinor components are interacting with each other, right? And one could, in principle, make the claim that this oscillation that you see here obeys, or it is somehow related to the temporal solution of this Dirac equation. Okay, that's a big step, right? We can discuss about it. Okay? So now the question is, well, this is really interesting. How is then that we're going to probe the dynamics of the system for topologically protected modes, which is basically the big feature of this Jackie-Breuer model. Okay? So then what we're going to do here, I'm extracting this figure from Dimitri's paper. Basically what we want to do, right? We want to couple this Dirac field, right, in a theory model to a soliton, right? So then we can obtain this zero energy state. Okay? And then basically the way it looks now, right, you have to create, they call it a kink. So we gotta get kinky to create this guy here, right? And then this will create this theory, right? Topologically protected mode that is stated here in red. Okay? So now the question is going to be, yes, good. The question is going to be, how are we going to create this kink in our atomic system? Right? So remember, the kink represents this scalar function that is changing as a function of time and somehow modified in last terms in the Dirac equation. So then basically the idea is we have to modify our quantum library interfaces to now add a tuning that is dependent on position. Alright, so basically this delta that in our previous experiments was constant and was providing us with the period of these oscillations that we just measured. Now we're going to change it versus space, okay? And the way we're going to do this is we're going to add some coils to our system. This is what is called gradient coils. Basically, you put your grad student to wrap them up. First one wrap, 1 centimeter later 2 wraps, 1 centimeter later 3 wraps, and so forth and so forth. So then you actually ramp the magnetic field. And you have to be sure that the magnetic field is placed in a certain way such that within the geometrical space in which the rubidium cell is, you have this dependence on the magnetic field. Okay? The claim is that if you can do this, right, this already kind of looks like this soliton that we have to use here to prove this topological method. Okay? So basically what we did, right, we transformed this a little bit. We have to open the beer can. This is what is inside the beer can, all these magnetic shielding, heaters, etc. And then these are the coils that we put inside, so that we can create this one here. I'm not going to make the story too long. Basically what we're doing right now, we are creating a Raman line. This is what you see here. And the Raman line is basically like the EID. You just go far the tune, and then what you want to do is basically when you apply the gradient, right? If you apply first at this same magnetic field, you will split this Raman line into two, right? And then once you have split it, then you apply the gradient. This is a test that the gradient works. If this split line that you see in red actually broadens, it means that the magnetic field gradient is working. Alright? And then basically, by knowing how much these Raman lines are broadening here, you can determine what is the magnetic field gradient that you're doing, basically by calibrating to the atomic data of the cell object. Okay? Okay, so this is basically working. We switch it on in an experiment and nothing happened. And then we thought like, oh yeah, topologically protected though. No, I think it was more like the experiment still doesn't really work. So then this is basically the status that we have at the moment in the experiment. You can always think of it as, remember we saw in these oscillations that the visibility of the oscillation is relatively poor. So then what we have to work at the moment is in making this visibility bigger, which actually means aligning the spin waves with respect to each other as much, basically very similar to what you do when you align two lasers to see an interference phenomenon. Okay? And then the second thing we need to try if, truthfully, by doing this position dependent seven shift, we can then get some topologically protected dynamic. Okay? Two words on the outlook that we're looking at. Remember, we discussed that we would like to do further quantum simulations in which you now have included also terms in the Hamiltonian that include terms of the form of the Kerr Hamiltonian, which is basically A diagram A, right, for different line modes. And then what we're doing here, I'm going to go into too much details. In my group, we also characterize how these room temperature devices operate as single photon nonlinearities. And we use a process that is called quantum process tomography to fully characterize quantum mechanically how quantum fields are modified by these Kerr nonlinearity systems, right? Basically what we can do is we can measure the phase that is provided to the electric field compared to the number of photons that is applied in the second field, okay? So we can do this. We cannot do it yet at the single photon level for both fields, but I guess after maybe it's possible to do it in a couple of years or so. And then if you can integrate these results, characterized very well using the photon nonlinearities, into these sort of preliminary Jackie model results, then we might be in our way to actually do some more sophisticated simulation of Hamiltonians that are more exotic, more interesting for different communities. Okay? With this, I'm just going to finish my talk. This is a small summary. This advertises, if you like this, now we have room temperature quantum light matter interfaces. Right? You don't need to make things cold. You can still make them quantum. We have 2 papers on this. Right? We talked about basically how we can bring the ideas of these EID quantum memories into the realms of quantum simulation, which is in community, and show you the progress that we have done in the last year or so towards building the quantum simulator for this Jackie model. Right? That's hopefully is coming soon, somewhere in this year or so. And I showed you that we actually have perspectives, right, to increase the capabilities of the system by adding single photon level nonlinearities. Some of this previous work is being already published. I just would like to acknowledge most of this work is being performed by my postdoc, Conor Kupchak, and by my grad student, Marina Massi, that you see here, very serious. And all the things that we did for the magnetic field were performed by Conor Bohan, which is a very good undergrad that we have here in Stanford. And well, with this, I'll thank you for your attention. I'm very happy to receive your feedback regarding this topic.
Thanks a lot, Aiden. Nice talk. Are there questions? Nala.
For this ready Jackie one, right? You are focusing on a wave equation.
Sorry?
You are focusing on a wave equation. So is it necessary actually that you work in the single photon level?
Let's say for the Jackie, no. Right? Actually, we do our experiments with many photons. But the point being that you can in principle translate these to the single photon level so that you can do things that are more sophisticated. This is just a starting point.
And the second question was for the nonlinearity.
Yeah.
As far as I know, the Figueroa is this optical depth in the system.
Yeah.
Related to single photon.
So
what is your...
Not necessarily true. The optical depth in the system goes between, let's say, 6, almost 10. Right? I think the Figueroa is more the interaction time of the photons while they're propagating simultaneously in the medium. Right? And this could be in principle controlled with a WAT system or something of that sort.
So I beg to differ.
Yeah.
Because I mean the interaction time of course can be increased by going to the solar effective interaction would also decrease.
So let's say basically our budget to increase this, let's say in the experiment that I show right now, you see a phase shift of about 10 to the minus 8 per photon, right? So that's where we are right now, so this kind of low. So the idea is I think that with these optical depths, just by doing, increasing the interaction time by a few orders of magnitude, and by doing heralding one photon, so you only measure when the phase shifts were truly created, I think that number can get into the single digits. We can discuss more about that.
Other questions? Michael?
So I have a question about this oscillation.
Yeah.
So when you have this counter-propagating EIT, you end up deciding this higher order spatial fluid, or deciding spin waves with higher order data vectors. Have you ruled those out in this theory?
Right. So then basically what we do, we have everything co-propagated. Right? So our system is similar to the counter-propagating proposal, but we do everything co-propagating with 2 colors. Similar physics, different physical system. What you see is when we detect the fields and then we see this oscillation, everything passes through a filtering system that actually has a spatial mode. Right? So the measurements that we do are filtering the spatial mode within our filtering system. Right? So what you say might be true, something that is present, but we are definitely filtering it.
Again, on these oscillations, these are related to this tuning from resonance used for coupling
Yes.
to PIT modes. And you mentioned the fact that the visibility of them is not very good. In fact, you can see that in the plot. I was wondering, you had also a blue line in the plot. Was that the fit to the data? Was that the theory?
Well, the one that has a fit to the data, right, of a very, basically, the only thing that we're doing is putting on top of an exponential decay, that we can calibrate what is the decay because we know what is the coherence time, and then we have this oscillation on top. Okay, and it is a fit, right? It's just like this is very preliminary data. As we said before, what he just mentioned is very important. The spin waves have a K vector.
Yes.
Right? So you have to align the K vector very, very precisely. If you do like a micro-radian misalignment, then those visibility fringes go down. So then the idea will be, this is kind of hard. If you can see these oscillations real time, you could increase, like normally when you align the lasers, try to increase the visibility somehow. Right? And this is basically the task of the grad students over the summer.
Other questions? If not, let's thank Edwin again. And let's move on. Next speaker.